Hi and welcome to a video where we are going to talk about infinite series, what they look like, how they work, and specifically we're going to look at two tests to determine if an infinite series has a sum or not. So a couple of things. When we talk about a series is what we call it when we take the terms of a sequence, which you should hopefully know a little bit about, and we add those numbers together. And we can have basically two types of series. We can have a finite series, which is kind of what we see here in this very first example. So we can see that this series starts at n equals 1, and so we're going to be plugging 1 in for n to generate that first term. When we plug 2 in for n, we get our second term. When we plug 3 in for n, we get our third term, and so on and so forth. And this is a finite series because it tells us to stop when n is 10, and we're only going to add those terms up. If you have a finite series, the sum of a finite series will always exist because you can always add those numbers together. Now, in BC Calculus, we primarily focus on infinite series. And so from this point forward, that's all we're going to talk about is infinite series. And you know you have an infinite series because we have our sigma notation, and you can see that we start at 1, but this time we end at infinity. And so this says we have an infinite number of terms that we're adding together. And the thing about infinite series is that sometimes that sum will exist and sometimes it will not. And so this chapter is all about determining, does the sum exist or does it not? And when a sum does not exist, we say that the series diverges. And this means that the terms add up to an infinite amount. If the series has a sum, we say that the series converges to whatever that sum is. And sometimes we can find the sum and sometimes we can't. So chapter 9 is all about determining, will an infinite series converge or diverge? So let's take a look. Here's a little bit of notation that we need to be comfortable with. We can see that an here, this refers to the rule or the equation that generates our terms. We refer to a1 as our first term when n is 1. Now n will not always be 1. Sometimes we'll have, like if n starts at 0, then we would start it at a0 plus a1 plus so on and so forth. So paying attention to that notation is kind of important as it will change kind of how the terms play out and what the terms are that we're adding together. However, I will say this. Whatever n starts at generally does not impact whether the series will converge or diverge. If a series converges from n equals 1 to infinity, then it will converge when n equals 4 to infinity, and vice versa. So let's talk a little bit about how to determine if an infinite series has a sum. The most basic way to look at this is we can determine the sum, or if the sum exists, by looking at what we call the partial sums. Now, a partial sum is exactly what it sounds like. Basically, we say the first partial sum is basically the first term. The second partial sum is what we get when we add the second two terms together. The third partial sum is what we get when we add the third term onto that. So as we add each term on, we get a list of partial sums. And so if we kind of look at our partial sums, and we're going to use the magic of computers and technology to basically put these little partial sums on the screen. So now that we can see these partial sums for these two series, we can see that the series on the left that I did in purple, those values, the partial sums, they kind of sort of look like they're approaching maybe a value of 1. And so we can kind of say, oh, this series seems to be converging to a sum of 1. However, the series on the right in red, you can see that those partial sums, as we keep adding the next successive term, we can see that the sums don't seem to be approaching anything in particular. And so we would say that, oh, this series probably seems like it's going to diverge. But how can we know for sure? Well, that's where we want to make sure that we are using convergence testing. And so we have a bunch of tests, and today we're going to talk about the nth term test and geometric series test in this video. So anytime we are doing a test to know for sure if a series converges or diverges, we want to make sure that we always do three things. The first thing we want to do is we want to state the conditions necessary for using the test. The second thing we want to do is we want to show the test. So since different tests are going to have different things we need to show, we're going to show the work and lay out a proof for how we know that a series converges or diverges, and then we always need to state our conclusion. And the conclusion is basically, therefore the series converges, or therefore the series diverges, based on what we show in step 2. But we need to always do these 3 things. So conditions, test, and conclusion. Those are our 3 really important things. So first things first, let's talk about the most basic test, and that's called the nth term test. Now, the nth term test looks like this. What are the conditions for its use? Well, we can really use it anytime. The best time to use it is always, and how it works is like this. This is kind of a tricky test because it's not really a test for convergence. I call this a divergence test because all this test does is it will tell me right off the bat if a series is going to diverge. And it works like this. If you take a series like this and you write out the terms, if the terms are getting bigger, and we're having an infinite number of terms that just keep getting bigger, for example, 1 plus 2 plus 3 plus 4 plus 5, that series is going to add up to an infinite amount. And so all the nth term test does is it says, hey, if your terms are not approaching a value of 0, then we know 100% that this series is going to diverge. So here's kind of how we want to lay out our test. We can use this for any and all series, and it looks like this. The series will converge, and if the series converges, then its limit of the terms, in other words, each individual term is going to approach 0. So if the series converges, then we know its limit must be 0, the limit of the terms. However, if the limit of the series or of the sequence of the terms is not 0. In other words, as those terms go on and on, as n gets bigger, if the terms are getting bigger themselves, then we know 100% that the series will diverge. Another example would be if the terms are turning into like a value of 2. So maybe you have like 2.5 plus 2.25 plus 2.125 and so on and so forth. And as those terms go down, they're approaching a value of 2. Well, if you have an infinite number of 2's that you're adding together, well, then the sum of that series is going to be an infinite quantity. So the terms must be approaching 0. If they are not approaching 0, then the only conclusion we can draw is that the series diverges. Now, if the terms do approach 0, it is really important to understand that the series may still diverge. So just because the limit of the terms is 0, that does not mean that our series diverges. So let's take a look at the 2 series that we just looked at up here. So just to kind of remind you, we did our partial sums and we said, oh, we think that this purple series on the left is converging to 1. We think that the red series on the right is not converging. We think that it's going to diverge. Well, if we take a look at these 2 series, and we kind of think about what the rule is for each of these series. The series here on the left seems to be the series 1 over 2 to the nth power. So this appears to be the series that we have. So 2 to the 1, 2 squared, 2 cubed, 2 to the 4th, and so on and so forth. So this is our series. Well, if I do the limit as n approaches infinity of 1 over 2 to the n, this limit is 0. Okay, so what that means is it opens the door. This series may or may not converge. This series, however, also has a limit as n approaches infinity. And if I look at this series and try to generate the rule, this just appears to be the series 1 over n. So when n is 1, when n is 2, when n is 3, 4, 5, and so on and so forth. And so if I take the limit of that rule, we also get 0. But we saw from the partial sums that it diverged. So just because the limit of the terms is approaching 0, that does not guarantee that our series will converge. However, if the limit of the terms is not 0, we can conclusively say that the series will diverge. So for example, if I look at this series here, so this is simply the series 1 minus 1 plus 1 minus 1 plus 1. And if we look at our partial sums, partial sum number 1 is just 1, but partial sum number 2 is 1 minus 1. It's those first 2 terms. Partial sum number 3 is going to be those first three terms, 1 minus 1 plus 1, and we're back to 1. Minus 1 again is 0, and so on and so forth. So our partial sums are going back and forth between 1 and 0. And so what we see here is that the limit of these terms, whatever the rule is that generates these terms, and I think in this case it might be something like negative 1 to the nth power. So what will happen there is if I start n at 0, that'll give me a positive 1 for that first term. When n is 1, that's how I get that negative 1. When n is an even power, it'll create those plus 1s. When n is an odd power, it'll create those negative 1s. Well, this limit really can't be determined. It actually doesn't exist. But the whole idea here is that this limit is not equal to 0. Therefore, we can say that the series will 100% diverge. In other words, we're never going to converge to a single sum. Now, the nth term test is something we always want to have in the background of our mind as we examine every series. We want to kind of keep it in the background, because what it can do is it can save us a lot of time and headache running any number of some of the other tests that we're going to learn along the way. And just if we can say, yep, we know that the series diverges, that saves us a lot of time. But if you forget to use the nth term test, we're going to be learning a lot of other tests that are going to definitively say yes or no if a series converges or diverges. So one of those tests that we really need to know, and probably one of the most important tests for infinite series, is identifying and using the geometric series test. So a geometric series is a very specific type of series, and it has to look kind of like this rule here in our sigma notation. So when I look at this rule, the way we learn it sometimes when we're first learning about geometric series is we identify what A is, and we see R to the n minus 1. Now, a geometric series is not always going to follow this pattern. You can have a geometric series with the sigma notation where you have like A and then R can be to the nth power, for example. And we might start our n at 0 instead of at 1. So you can have a geometric series that looks a little bit different. But the thing we want to look for is we want to find a sigma, and then we want to have something to a power of n, and maybe there's a constant on the outside, but something to a power of n is generally going to indicate that we have a geometric series. Now, what a geometric series does is it takes these terms, and each term, to get the next one, what we're doing is we're multiplying by something called that common ratio. So we can see that if we write out the terms of a geometric series, we're multiplying by this value of r. So we have a plus ar, and then each time we're multiplying by r to get the next term. That's where the r squared, the r cubed, and so on and so forth come from. And so for the geometric series test, the conditions that we need to be able to use this is we have to have a geometric series. The best time to use it is when we have a geometric series. And here's how it works. If you have a geometric series, you know that your geometric series will converge if that value that you're multiplying by, that common ratio r, if the absolute value of r is less than 1, then we know that the series will converge. Now, how do we know that the series converges? Let's just take a look for a moment. If I have a series where I have, for example, 1/2 to the nth power, and I start n at 0, my series looks like this. I have 1 plus 1/2 plus 1/4 plus 1/8, and so on and so forth. Notice that my terms are decreasing in value, and so just kind of thinking about that nth term test, that gives me a chance to let this series converge. Now, it doesn't guarantee that this series converges. The geometric series test is what allows us to guarantee convergence, and we'll play that out here in just a moment. But if I had a similar series where my multiplier, my r value, was something like, I don't know, let's just pick 2. We'll keep it nice and easy. We'd have 1 plus 2 plus 4 plus 8 plus, and so on and so forth. And we can see that the limit of these terms, as n approaches 0, it's going to, or as n approaches infinity, is going to fail that nth term test. So the terms aren't decreasing, so it 100% is going to diverge. When we have a geometric series, though, we can be a little bit more explicit with our convergence and understand that if we have a geometric series, as long as that r value is less than 1, we will 100% converge. And what we converge to is found by using this formula here. The sum of an infinite geometric series is a, and a is going to be our first term. So first term here. And r is what we call our common ratio. It's our multiplier. So let's take a look at a couple of geometric series and see how this little test works. So, do the series converge or diverge? Well, when I'm looking at the series, let's look at our first one here. First of all, this is a geometric series. I know it's geometric because I have something to a power. My r value is 1/2. Now, to find the a value, I have to be really careful. I know sometimes when we first learn geometric series, we are taught that that number that's out in front is our a value. It's our first term, but it's not always guaranteed to be that. In order to find our first term, we have to get in the habit of plugging that first number for n in for n. So when I put 1 in for n, I get 3 times 1/2 to the 0 power. Well, sure enough, here my first term just happens to be 3. But it's not always going to be that way. So what we're going to do here is we're going to say that this series converges as a geometric series. We're going to identify it. And we're going to say because we're going to identify what r is. R equals 1/2, and that is less than 1. Then we're going to find the sum. So we're going to take that a value, that's that 3 that we found when we plugged in that first number for n, and we're going to divide it by 1 minus r, 1 minus 1/2. When we simplify, we get 3 divided by 1/2, flip that fraction, multiply by the reciprocal, and we get that this series converges to a value of 6. So let's keep going. Let's take a look at another series. How about this series right here? So first of all, I'm going to identify it as a geometric series. I have something to a power of n. This is a geometric series. Now, it doesn't matter that the value inside is negative. That's okay. This is still my r value. It's -3/5. Now I'm going to find my a value. A is what I get when I plug in that first number, n. That's going to be my a value. So a is going to be -3/5 to the 2 minus 1. That's just the first power. So a just happens to be -3/5 as well. Sometimes that's how that works out. So I'm going to state my convergence. I'm going to say that this converges as a geometric series. Because r is -3/5. And here, because it's negative, I'm just going to be a little more careful. I'm going to say the absolute value of r is less than 1, because the absolute value takes care of that negative sign for me. All the negative does is mean that it's going to alternate as I add those terms together. It's going to alternate plus minus, but it's not a big deal. So what is my sum? Anytime I have a geometric series, I want to find the sum. So I'm going to take my a value, which is -3/5, divide it by 1 minus my r value, and then I'm going to simplify -3/5. This is going to be 1 plus 3/5. I'm going to get a common denominator. 5/5 plus 3/5 is 8/5. So I'll have -3/5 divided by 8/5. Flip, multiply by that reciprocal. The 5's will cancel, and my sum is -3/8. So again, geometric series, this is how we want to be able to find those sums and determine if the series converges. So what happens when we have a series that is not necessarily written in sigma notation? Well, what we want to do is we want to try to figure out what is the rule that's generating these terms. So I kind of always start out by saying, all right, well, this must be n equals 1, this must be n equals 2, this must be n equals 3. And so I kind of look at the top and the bottom and try to figure out those patterns. The top seems to be pi to the nth power. The bottom seems to be 2 to the nth power. And anytime I have a power over, something to the nth power over something to the nth power in the denominator, I can rewrite it as pi over 2 to that nth power. So I can kind of take that power out and use those properties of exponents. So here, it looks like r is pi over 2, and our a value also happens to be pi over 2, so that's my first term. So when it's written out like this, it's really easy to identify what a is. And so now I can say that this series converges, or does it? Let's see. If r is pi over 2, let's kind of back up here, and we get it's really easy to kind of get swept up into the momentum here, and I almost got caught up myself. But if I look at what r is, I have to remember pi is about 3. And you guys, if r is pi over 2, that means that r is approximately 3/2, or approximately 1.5, which is bigger, not than 0, it's bigger than 0, but it's bigger than 1. And so we have to be really careful and mindful and always be looking at what r is. This series actually diverges since r is pi over 2, which is bigger than 1. And that's all we have to say. So there's no sum here to find. I just have to say that the series diverges and also say why. Let's look at one last series here. So here I've got something, it's not quite geometric the way that we have been seeing geometric things, but this is actually a geometric series. And sometimes we have to be kind of on the lookout for ways to make something geometric. So remember I said if you have something to a power over something to a power of n divided by something else to a power of n, you can kind of reimagine the rule and use some algebra to make it appear more like that geometric pattern that we're used to seeing. So I notice that I have 2 to an nth power. The plus 1 doesn't bother me, but then I have 5 to the n. And so this looks almost geometric the way that I'm used to seeing it. But let's see if I can take this rule and rewrite it. See, 2 to the n plus 1, I can rewrite it like this, 2 to the n times 2 to the 1. And if I rewrite it like that, I can remove that 2 to the 1 power, put it on the outside, and then I have 2 to the n over 5 to the n. And then just like we saw with that previous example, I can take that power of n and put it totally on the outside. And so now we can rewrite this in a slightly different format to be able to identify what r is. And so r is going to be 2/5. A, did not mean to do that, a is going to be what we get when we plug 0 in for n. So we'll have 2 and then 2/5 to the 0 power. So we want to take that first value of n and plug it in for n. That's always how we get a, and in this case we do happen to get 2. It's not always that number on the outside, but now I have a, I have r, and because r is smaller than 1, I can find that sum. So I'm going to go ahead and state what's happening here. This converges as a geometric series because r equals 2/5, and that's less than 1. And then the last thing I have to do is to find my sum. So s equals my a value, which is 2, divided by 1 minus 2/5. That's going to be 2 divided by 3/5. My sum is going to be 10/3. So this is just your reminder to be on the lookout for numerators and denominators that have powers of n, and just kind of looking for those ways to be creative with your algebra and rewriting the expression so that you can tell what r is and then find that value of a to be able to determine, does the sum exist, and if so, what is it? So one last example, and this example is a little bit different because this example is a geometric series. What are we multiplying by? Well, let's take a look. I'm multiplying by 2 to get to my coefficients, but then you'll notice that the powers of x are also going up. So here I'm actually multiplying by 2x each time. So in this case, my r value is 2x. So this is a little bit different type of geometric series. This is actually something called a power series that we're going to be looking at in the next part of chapter 9. But with a series like this, we have to think about, wait a minute, this is geometric. Are there restrictions on what x can be in order to create a geometric or a convergent geometric series? Well, we know that r has to be less than 1. So I'm going to put absolute value bars around this and say this has to be less than 1 to converge. Okay, so, well, let's just kind of solve this little absolute value equation. So if the absolute value is less than 1, another way to express this is we say that negative 1, 2x has to be between 1 and negative 1. That's what it means to have an absolute value be less than 1. So we kind of drop those absolute value bars, re-express it as a compound inequality. And then basically if we solve this little compound inequality by dividing all parts of the inequality by 2, so we can get x alone, we find that as long as x is between positive and negative 1/2, we will have a list of numbers that converges. So if we pick a number that's outside of that 1/2, so for example, if I let x be 1, then my series will look like this. I'd have 2 plus 4 plus 8 plus 16 plus dot dot dot. And we know that if x equals 1, that series will diverge because those numbers are getting bigger and bigger and bigger. But if I have a value of x that is smaller than 1/2, so for example, let's say that I let x be 1/4. Well, then I'm going to have 2/4 plus 4 over 16 plus 8 over let's see, 4 to the third power is 64. And I will be able to have these terms, and notice they are going to get smaller and smaller, and this will create a series that converges to some sort of a sum. Well, what is the sum? Well, we just simply use our sum formula. So we know that a geometric series always converges to a over 1 minus r. Well, a is your first term, that's 2x. R is 2x also, sometimes they're the same thing. But essentially, it will converge to whatever this function is. So when x is 1/4, my sum will just happen to be 2 times 1/4, and then 1 minus 2 times 1/4. Whatever that works out to be, that'll be my sum when x is 1/4. So it's kind of cool. We get this little function that tells us our sum when we have a geometric series like this with an x in it. And again, that's called a power series. But that's something for later on, just a little taste of what's to come. So in kind of closing here, whenever we're looking for an infinite series, we want to know if it converges, that means it has a sum, or if it diverges, that means that it adds up to an infinite quantity, or maybe nothing at all. And when we are looking at our infinite series, we want to first check that nth term test and make sure that the terms are not approaching something other than 0, because that's a really great way to save ourselves some time and say, oh, yep, if the limit of the terms is not 0, then the series will diverge. However, if the limit of the terms is 0, that doesn't really help us. But then we can go on and we can look to use a different test. And so in this video, we talked about one test that you can use, and that's the geometric series test. So always be looking for ways to determine, is my series a geometric series? And if it is, do I know that it converges? And if so, what does it converge to? We're going to use that sum formula. So now you are ready to tackle some geometric series and find if they converge or diverge. You got this.